Well, it's certainly a pleasure to be here in London. It's been a while since I've been here, and we had a great tour organized by Mike yesterday for parts of London I never would have thought to investigate on my own, and really enjoyed it. A couple of small things before we get started. First off, Phobos now compiles with DIP 1000. So that's a huge milestone. I don't know quite yet if Seb has integrated it into the main line, but it's there, and we did it, and we made it work. So that's good. And the second thing is a very huge thing that has happened just last week. GCC, the GNU compiler collection, has released D as one of their standard packages. This is an enormous boost for us. And it's all due to Ian. Can you stand up, please? Ian is a man who's worked for years and years, toiling away basically by himself. It's a monumental achievement and a huge achievement for D in general to be part of the GNU compiler collection. So, on with what we're talking about, allocating memory with the D programming language. Fun topic. Lots of keys to getting your programs to run faster. You know, better algorithms, low-level optimizations. People talk about this stuff all the time. Code caching, multi-threading. But today we're going to talk about the big thing for improving your performance of your code and all that is allocating memory. D sometimes as people think that D is a garbage collected language. I hope to disabuse that notion in this. D has a large number of techniques available to you for allocating memory. Even within a single program, there's no reason why you can't use multiple methods of allocating memory depending on what you're trying to accomplish. And the different techniques for memory allocation can have a dramatic effect on your program, effects on your memory consumption, performance, how easy it is to write programs, robustness for bugs, things like that. So I'm going to go down some of these. First one is automatic memory management, and we all know our friend Autopilot. We all know what this is. We allocate memory, and the runtime takes care of managing it for us. It has lots of advantages. For one, it's easy. You just allocate memory and you use it, and you don't worry about it. It's completely memory safe. It's fast to write code, and on a more technical issue, it handles cycles. And of course, everything has its disadvantages. Automatic memory allocation consumes roughly 3 times the memory. Depends on how you use it, but you can generally count on it eating about 3 times the memory of what is actually being used. Probably the worst problem with it is it does a pause while the collection runs. And if you're using interactive programming and it pauses in there, like running a game, this is a problem. For example, I use the Thunderbird email system, and when it's doing a memory allocation, the program just freezes. And you don't know if the battery died on your keyboard or what's wrong with it, except I've learned to wait about 10 seconds and then it comes back. So it's not the best user experience for applications. The next problem with it is resource management. It's not really determinate when the destructor is run on your data. It gets run when the collection is done and it frees the data, which happens at an indeterminate time. So you really don't want to use garbage collection for resource management other than memory. And the last problem is long-running programs can run out of memory because the way the collector works, it looks for references to memory. And if it cannot find any references to memory, it frees it. But sometimes fake references can exist to the memory, and the collector doesn't know they're fake references, like an integer that looks like a pointer. And you can run out of memory from that.
So
I'm right.
Did some benchmark on that a few years ago, and it turns out that this is a real problem on 32 bits, but this is not that much of a problem on 64-bit architecture anymore.
Which problem?
Like having false pointers?
Having false pointers, yes.
The rate on 64-bit architecture becomes very, very, very low.
I'm sorry, folks, do we have a mic for the questions?
Well, I'll repeat it. Basically, he's saying that with a 32-bit address space, you're much more likely to have aliasing problems where random data looks like pointers than on 64-bit systems. And so going to a 64-bit system has greatly alleviated that problem, but it's still, even if it doesn't exist practically, it exists theoretically. And if you're interested in guarantees, it's still not giving you a guarantee. It just kind of pushes the problem into the background. And if you're really a purist or you're running a critical system, you kind of want a guarantee, not just saying it's unlikely to happen. So yes, indeed, going to 64 bits has reduced a lot of these disadvantages. So when would I choose to use automatic memory allocation? It works great for scripts. There's a reason why scripting languages don't use malloc, is because you're just running a little script. Who cares? You allocate memory, you use it, and lots of times you don't even know you're allocating memory the way you write scripting code. And D, as Andre has figured out and demonstrated, is actually a very good program, very good language for writing scripts. If it's a larger program that's not a script, you can use the garbage collector to allocate memory for the parts of the code that is rarely run, like the initialization code. There's no reason not to use the garbage collector for initialization code. It can waste a little memory. It does not matter. Error handling code, you can also use the garbage collection because generally your programs run without errors, so using the garbage collection or the automatic memory management for error handling is a convenient thing to do, and it does not matter if you're using it. Batch utilities are programs that do not have a user interface. Who's got an idea what a batch program, or a classic batch program is? Yes, way in the back. Yeah.
Well, you just put your punch cards, you come back the next day, and you see if the result is what you expect or more likely.
That is the origin of the term batch program, is it actually was a batch of cards that you submitted. But, and you got to, what is a classic batch program that you guys run all the time?
Compiler.
The compiler is a batch program. There's no user interface to it. You run it, and it runs, and it stops. It's not a long-running program. Garbage collection is actually a fairly good strategy for that. It's also a good strategy when your developer costs greatly exceed your compute time costs. So if you're running a program that's going to run on a server system where you've got to handle enormous amounts of requests and things like that, automatic memory management can be a problem, and you probably don't want to use it for that. But if you're just want to write a program that does generates reports, garbage collection is perfect for it. It's perfect for programs that are one-time use, like I just need to, when I was working on my taxes, I needed to write a program to go through the accounts and do some sums and stuff, and automatic memory management is just absolutely perfect because I really want to concentrate on getting the right number to put on my tax returns. I didn't want to be worrying about who owns the memory. Nobody wants to worry about who owns the memory when you do that. I just want to go, I want to allocate the memory, add up the numbers, print the right result. Who cares about ownership issues? I don't want to deal with them. Automatic memory management is absolutely perfect for that sort of thing. By the way, guys, you can pop up and answer or ask questions anytime. I kind of like these things to be interactive. So the next technique is, of course, one we all know, love, and hate, which is malloc and free. And malloc and free is, of course, much maligned, but it has its advantages. Everybody knows about malloc and free. Everybody knows what it is, how it works, it's well understood, it's fast, it's compact, it's well implemented. I mean, generations of programmers have written malloc and free and tuned it and stuff like that. And it has a great feature that it interoperates with C code. You can call malloc in C and free it on the D side, and on the D side you can malloc and then pass it to C code, and the C code will free it. So that is kind of at the opposite end of the spectrum from automatic memory allocation. Okay, the disadvantages are also very well known. Doesn't do any memory safety checks. You can have dangling pointers, memory leaks, double freeze. It turns out that this code is very hard to audit. There was a pull request recently on D where somebody adjusted some of the code that did memory allocation, and in some cases it would do a double free. So it's just hard to get that right, and it's fragile. And when people come in and modify the code, sometimes they don't take care with it, and bugs can be introduced, and they're ugly bugs when they happen. Who's had this happen to your code? Somebody comes in and changes it. Yeah. Everybody who's programmed in C has had this problem. Malloc and free is great when the time your program is running, or you need every erg of C, is worth a lot more money than your programming developer time. Developer time is expensive, extremely expensive, because I'm sure all you guys are very well paid in the industry. But when your programs are costlier than you are, then malloc and free starts becoming more justifiable. It usually works only if you've got experienced developers developing the malloc-free code, though that's kind of a chicken and egg thing, is how do your programmers get experienced at using malloc-free is, well, by actually doing it and starting out as inexperienced developers. I also wouldn't use malloc and free when your program fails, it's going to be a disaster. You don't want to use it on your avionics system and have it mess up your avionics system. You don't want to use it on your trading software and find that buffer overflow has caused you to buy, 1 million shares of Enron just before it crashed. And of course, you don't want your application to be a vector for malware and show up on /dot as a buffer overflow exploit in your code has caused a lot of people a lot of trouble. But one cool thing about malloc and free is you can customize it. And you can customize it to do cool things like instrumenting it. For example, putting in counters to see how much memory am I allocating, where am I allocating it from, what am I using it for, where I'm freeing it. And this can be very useful for trying to optimize your memory usage and improve performance. You can do things like add sentinels. What a sentinel is a sort of a known memory value at the beginning and end of what you allocated. And if those things change, you've got a memory corruption problem. Of course, different kinds of allocation strategies can be used depending on your particular application. And there's always all those people who worked on malloc and free are idiots. I'm a better programmer than they am. I can make it faster. And that is always a fun challenge. And malloc and free, and don't think it can't be done. Because people have thought for a long time that malloc and free was done perfectly, and then they came out with jmalloc, which turned out to be a lot faster. So as Andre would say, there's always more oil in the olives in there somewhere. And it's a good exercise, how good a programmer are you? Can you see a way to speed up malloc and free? Okay, well, I just got through saying that memory safe malloc was impossible, but it isn't impossible. And I think Mike says we have a t-shirt to give to the person who can tell me how to make malloc memory safe.
You name it free.
Too easy, oh God. But, Mike, where's Mike? Amare gets the t-shirt. He saw through my little joke a little too quick. No smart people allowed in here, get it? Okay, there is a trick, and it's just allocate never free. And that little insight actually is very useful when you're thinking about memory allocation is because it points out just why malloc and free are memory safe. It's not the allocation that's the problem, it's the freeing that's the problem. And it's useful for batch processing like, like compilers, I'm sorry. And DMD compiler is well known as using this technique. It just allocates memory and never frees it, which for a long time I thought 32 bits of memory, we'll never overflow that. Boy, was I wrong. 32 bits of memory ought to be enough for anyone, right? Turns out it's not enough. And so there have been sort of slow attempts to integrate into the front end some more frees, which come at some risk, like I mentioned earlier. There were some mistakes introduced with that. Or you can switch to a 64-bit compiler, but still, if it uses lots and lots and lots and lots and lots of memory, your program gets slower and slower and slower and slower as it starts thrashing. Anyhow, it's really fast, and you can also use it for any program, any data you need that's going to last till the end of the program. There's no need to free memory and then exit your program, because the operating system is going to throw it all away anyway. There's just no reason to do that. So if you're initializing data structures, you just malloc and never free, and you're perfectly memory safe. Here I put together some code that actually implements your own alloc and free, and we'll see that the free simply does nothing. And don't worry that the function is just going to be a return, because the compiler will inline that and do nothing with it. But it's really pretty simple. It allocates code in chunks. It does 16-byte alignments, so 4,000 16-byte chunks, and allocates a chunk, and with a couple of globals, it keeps track of how much memory is used. And it's actually much faster than malloc as well, because all it does is takes a pointer, returns a pointer, and moves the pointer down by how much memory you allocated. And it's called a heap allocator. And a couple of interesting things about this is its use of nested functions. So right here is the nested function. Happens when the allocation fails for whatever reason. And the nice thing about it is it gets called twice in here. both really when the malloc fails to allocate us more memory, we need to error. And that's common code. And nested functions are a really fine way in D to factor out common code. So that's what that is. And it even has a goto in there. You know, it's like the shame. But I justify it where you want your heap allocator to be really, really, really fast. So the code layout is so that the most common case is the straight-through code, and everything else uses gotos to try to, well, straight-through code tends to run faster, and everything, the style of this is all bent towards the straight-through code is the fastest, as the most common case, and everything else is done with gotos. Like the error code, you know, sure it calls a function, but who cares because your program has failed anyway when malloc has run out of memory. The next thing is an idea that was popularized by Andre. Andre, who is your co-conspirator with ScopeGuard? Petro, yes. It's a great idea. It's a method for hooking all the exits to your function and attaching some code to it. So what would we hook on the exit to our function? Free. So it gets executed regardless of how you exit the function through a normal return or by throwing an exception. You might think, well, this sounds like try catch finally, and you'd be right because it's actually rewritten internally to a try catch finally in a process called lowering. Lowering is when the compiler rewrites high-level constructs into low-level ones. So what this means is in the compiler, you only have to get the implementation for a try catch finally right, and then ScopeGuard implementation is going to be right. The nice thing about the ScopeGuard is you can put with try catch finally, you allocate memory, and then way down in the finally, or the catch, is the free. But with ScopeGuard, you can install your free code right next to where you're thinking about it. So the malloc and the free are paired close together, and this only gets executed when your function exits. Or even your scope exits. It's not just the end of the function, it's the end of your curly brace scope. I really like ScopeGuard. It has a natural, clean syntax. It, nails the dreaded and perennial bug of somebody comes in and adds another return into your function and forgot to free the memory. And it also, not many people think about making exception-safe code, and they don't free the memory when an exception's thrown, and this takes care of that problem too. But it's still, the other problems with malloc free are still with us. It only deals with one of the issues. The next one is...
Excuse me.
What? Oh.
All right, sorry. Regarding scope exit, I want to note that there is a horrifying open bug about it, and probably best way can be used with C functions at the moment. It's not safe to call elaborate D functions that may throw a second exception inside the scope exit block, or generally inside the finally block, because you may run into very horrifying crashes because of an open bug with exception chaining. Just wanted to note that. Be very careful about scope exit at the moment.
All right, another way to think about it is don't throw exceptions when you're unwinding. That's actually my preferred solution. There's not a whole lot more confusing than trying to figure out what happens when you're throwing exceptions inside an unwinding. Trying to think exactly what's going on in there. C++ deals with that by just terminating. if you do that, which actually I think that method has a lot of merit. But yes, thanks for bringing that up. Okay, destructors. You read that, it says core destruct there, so. This is how it works. You allocate in your constructor, and in your destructor, you free it. It's RAII stands for Resource Acquisition is Initialization, which is one of the most awkward acronyms ever invented. In D, we don't use acronyms. We use names like Voldemort types, which are a little bit more whimsy on it. And so we've hidden the allocation inside the struct and our freeze in that. And well, that's a significant improvement. It's the way C++ does things. It also happens to be very well understood. It's exception safe. There's the old nobody ever got fired for using RAII because it's so commonplace. You still have problems with dangling pointers. It only works when you have one owner of the object. If you have multiple owners of it, then you don't know whose job it is to run the destructor. And if your data structure has cycles in it, it really doesn't work at all. But the cases that it does work in is actually pretty large, and it's effective. So, get into reference counting. Whenever I think of reference counting, I think of a miser, counting his coins. Because that's kind of exactly what it is. You're being a miser with memory, and you're counting your coins. And here's an example of how to implement it. Unfortunately, it's a little more code than the other one. But what it does is it does two allocations, one for the actual data you want to deal with, the payload, and that's the first one. And the second one is it creates an allocation for the reference count. And then when you have the copy constructor here, it increments the reference count. And when you free the object, if the reference count goes to 0, then I can free my payload and also free the reference count. And the tricky part is if I assign one to the other, it means I have to release the old memory and increment the reference count for the new memory. And there's a trick in this. You want to release the memory after you've done the assignment. Otherwise, you could wind up doing the assignment and mess up the reference count. And so you really want to do the free of the original value as the last thing in there, although it seems like you could do it at the beginning. And the reason for that is you have self-assignment, A equals A. If you don't do this last, you'll wind up doing a double free. So Razvan is doing a talk on copy constructor, and one of our big motivators for doing copy constructors is now we can properly support reference counted objects in D. So really looking forward to hearing that talk from Razvan. Reference counting is boring, right? No questions? No, that's the greatest idea? Okay. Well, hopefully maybe we'll get to some more fun ways of allocating memory. Of course, reference counting has no pauses. Memory is reclaimed as soon as possible because the miser knows exactly how many coins he's got. And it also has disadvantages. If you have a circular data structure, reference counting doesn't work because, again, you get into the problem of who actually owns that memory when you've got a circle in your data structure. One of my pet peeves about it is it's expensive due to exception handling. Whenever you have a destructor being run which decrements the reference count, what happens if an exception is thrown in there? You have to catch the exception and decrement the count and then rethrow the exception. And that means it's expensive to set up the exception handler for the reference count, and it's slow. Attila.
I can never find the paper, but I read somewhere that actually reference counting can trigger pauses if you happen to get the reference count to 0 that causes another object to go to reference count 0, that, et cetera, et cetera, et cetera. So shared pointer even in C++ could actually trigger a pause, which most people seem to think is magical.
You are quite right. Malloc and free generally is thought of as having no pauses, but that's actually false. Because malloc can run out of memory locally, which means it can then needs to call the operating system to get more money. The operating system may need to start causing paging to happen, is flushing other things to memory. And, you know, there can be a cascading set of things happening that you cannot put a guarantee that it's within a bounded time on that. The only real way to get bounded time on memory allocation is to pre-allocate things. So, and then you know that it'll be a bounded time. Amara.
Yeah, so one of the idea I've been playing with, but I'm not quite sure to implement it in practice, unless hacking the compiler itself. So it would be to use reference counting, but allocate the memory on the garbage collector anyway, and not decrement the pointer when you throw an exception, which keeps, like, essentially you never leaks except when you throw an exception, but you get into a position where it's cheap again to throw exception, and because exceptions are usually exceptional, and if they're not, you have other problems anyway. Usually it's good enough because you don't leak that much, and so you don't really pause that much.
That's actually an interesting idea, and I hadn't thought of it, so thank you for bringing it up. The idea is to not worry about maintaining your reference count through exceptions, and that way you don't have to put an exception handler around it, and then let the garbage collector handle it in the future. So that's one of the cool things about having an automatic memory manager in the compiler or in the language. It can be used as a backup. Even if you don't use it, it only happens in exceptional circumstances, and you know, it's quite nice. Lots of times RAII has been sold as being zero cost in the non-exception throwing case. And this is just simply false. It is not zero cost. And if you examine the code generated for your RAII destructor call, it is significantly worse than the code if you did not wrap it in an exception handler. One of the reasons is most compilers, in fact nearly all of them, just simply throw in the towel on optimizations when things are in the exception handling try or catch and finally blocks. The register allocator won't allocate registers across exception or the scope boundaries. The data flow analysis just does not work across those. So I think it's been a little bit oversold as being zero cost. It's not zero cost, it's rather expensive. Another problem with reference counting is if your object can be shared, the increment and decrement have to be protected with locks. And in high-speed applications, you really don't want to constantly be doing locked increments and decrements. So there's a cost to that too. And ironically, it can even, if you aggregate the pauses in your automatic memory management, it's actually less aggregate time than you're spending in the reference counting scheme. It's just that people don't notice it with the reference counting scheme because it's spread finely and thinly throughout your whole program, which makes it a much better solution for a user interface to do reference counting, because people won't notice millisecond delays, but they will notice the 10-second collection cycle, even though the overall program is running faster. Okay, stack allocation. When I was in college, I was reading the PDP-10 instruction manual, and it kept talking about a stack, and I had no idea what a stack was. And so I asked a friend of mine, what's a stack, and what is a program stack and all that? And he says, well, it's like a bunch of dinner plates. You put dinner plates on top of the stack, and you take dinner plates off the stack. And it was a perfect analogy. So whenever I think of stacks and all that, I always think of a stack of plates, or, you know, an even more favorite term is a stack of pancakes. You're supposed to laugh. Okay, so much for my second job as comedian. I better stick to compilers. So here's a technique I commonly use is I create a buffer on the stack with some arbitrary dimension to it, and then when I know the length of what I need, I slice it like this. It's really a simple technique, effective, and don't forget the equals void. Because who knows what happens if you forget the equals void?
A lot of T constructions.
You get a lot, every one of these entries gets initialized, which is, if you've got any speed critical code, that's really going to slow you down, and it's a bit invisible. So don't forget the equals void. It has great advantages. It's about as free as you can get with memory allocation, because the compiler or the CPU is already moving the stack pointer. It just moves it a little bit further. The cleanup when the function leaves is no cost at all. It just resets your stack pointer. You don't have to worry about exception handling. And emphasize, don't forget the equals void if you're using this technique. Okay, here's the, everything has disadvantages. The buffer is always going to wind up too small in some cases. So when it's too small, now you got to add error handling code, and what are you going to do about it? And the error handling code can be messy and annoying. And the other problem is, if you allocate too much on the stack, you can run out of stack space, which happens on embedded systems that don't have a lot of memory, or if you're running lots and lots and lots and lots of threads, you can easily run out of stack space on them. Okay, which comes out to how are we going to deal with that? A better way of dealing with running out of memory on our stack allocation is, our hybrid stack malloc routine. That's actually a real thing. Anybody know what it's called? I forgot. A quagga? That sounds familiar, yeah. This looks like something a mad scientist would do. So here's how it works. We see this is the same code we had before. No, we didn't forget the equals void. And if our length fits, we just slice our stack buffer. And if it doesn't fit, we fall back to malloc. And at the end, we have, if we malloc the pointer, we have to remember to free it. And of course, you can use RAII and all that stuff on there too. But I wanted to show the dirty laundry and how the thing works under here. Now this is the interesting thing is you want to make sure you test the malloc path. Because if, we all know what happens with untested code, it doesn't work. So what I like to do, and I use this technique all the time, you'll see it in the compiler source, is I have a debug version of the length, which is very small, to force it to always, or to at least try out the malloc path, so I know that it works. What value do you pick for it? Well, I just put a print statement in there and run some typical code through and look at the values it's allocating, and then I pick a value that encompasses most of them, so only very rarely does it actually malloc. I use this technique a lot in the Warp C preprocessor, which was extremely fast. It used this technique all through the code, and I spent a fair amount of time just putting the printf in saying, how much do I really need to allocate this when I'm compiling boost code and stuff like that. So I was able to get the advantages of my fast stack allocator and almost never called malloc, and it was one of the secrets to the huge speed of the Warp preprocessor I put together. Okay, now we're getting into more fun stuff, and I couldn't find a picture. I apologize. Yes?
I got a question on the stacking one. Right? So a question on the, also the hybrid actually. Why could D be extended to allow a dynamic length for that stack allocation instead of the 100 that you had earlier? What if there is an integer there that?
Are you talking like the alloc that's in C?
Yeah, exactly.
Okay, the reason I don't use alloc, this is a great question by the way, is because it tends to be erratically implemented. And it's a really hackish thing. It doesn't actually work as a, oh my God. I thought I was moving too slow. Okay, there's a lot of trouble with alloc. It can't be lowered to regular code. It requires a magic in the back end to generate the right code for it. And I just prefer to avoid that using alloc, because some C compilers it's there, some it's not, some it's badly implemented. This one I know how it's implemented and I have predictable results. So that's why I prefer this. Okay, hybrid stack malloc with Voldemort types. This actually encapsulates that whole stack allocation and malloc allocation into a struct. And struct call result, which is a nested struct, which makes it a Voldemort type. I create my buffer by calling this function here. And calling this function actually allocates data on this function stack. And it does that through the magic of what's called a named return value optimization. And this is actually used a couple places in the compiler. It's a more advanced technique, and it's real cool because it completely encapsulates all this messing about with malloc and free. And all the user sees is this one little statement, allocates the memory and cleans up after itself on the stack. What?
Won't it crash if it ever gets copied?
Name value return optimization doesn't copy.
I know.
It actually writes this directly into the stack frame of the caller.
I know, but if for some reason it ever gets copied, it would.
Right. Well, anytime you do stack allocation, yes, if it escapes the stack, it will crash. And that's what DIP 1000 is there to do. But I didn't want to have a talk on DIP 1000 because it's a whole talk in itself. Okay. So that. Chain. Now, chain is how to allocate memory without allocating memory, which I think is the coolest allocation technique. It doesn't do any allocation at all. It manipulates things using ranges and slices. Like slices, it's extremely efficient, and it has very predictable performance. So what I want to do, how many people take, file name and concatenate it with a path? Everybody, okay? You do it with malloc, right? Yeah? Well, you don't have to actually use malloc. You can call chain. Path, file name, and then I can use for each to loop over it and print out hello Betty in there. And here's how it works. You have two strings in there, and the range functions are empty front and pop front are all like, which of these slices am I looking at? And I combine the two and call it chain. And I think this is really cool. You don't have to, there's no memory allocation. You don't have to decide what memory allocation you're going to do. You don't have any trade-offs. Since it basically works as slices, the same issues you have with slices apply, like your chain cannot last longer than the data it passed in. So you got to watch your lifetimes. The implementation I showed here, I had to ruthlessly pare it down to fit on the slide. So there's a more fleshed out one in the standard library called chain for more general implementation. And so there we go. So here, D is not just an automatic memory managed language. It has a whole bunch of options on how you can allocate memory that is specific to how you want to do it on the needs of the specific part of the program you're working with. And they all range from complicated to very simple. So, any questions?
So I work with a number of developers who try out different languages like Rust and Go and D as well. And some of my Go friends have made me aware of the fact that they've undergone significant garbage collection improvements in the past maybe 3 years. And they're getting, they claim, about like 99.9% on average sub 10 millisecond latency on their garbage collection. Is there anything that stops D from getting similar performance? Because the automatic garbage collection is extremely convenient for developers.
Yes, you're right, it is extremely convenient. What stops D from having an automatic memory management like that is a thing called a write gate, which means every time you write through a pointer, you have to notify the garbage collector that this piece of memory has changed. And D, with its stack allocation, really doesn't need. Well, the write gates will slow things down because every pointer write is going to have to run through the write gate. So there's a performance penalty to that, which is made up, of course, by improving the garbage collection. Well, I didn't put write gates in there, and I think it's a poor trade-off for D because it's a systems programming language, and I think that such a penalty for every pointer write is completely unacceptable. And the trade-off, of course, is the automatic memory allocation isn't as fast or as effective. But you have all these other techniques, so when you need the allocation to be fast and effective. So, Razvan.
DMD uses a lot of memory, and sometimes even in our testing pipeline, it runs out of memory when it compiles Phobos. So are there any plans on maybe getting DMD to be garbage collected or freeing memory? Because even though it's very fast, it brings some problems.
I've tried it with using automatic memory management, and it slows down dramatically when it's using that, and so I kind of abandoned it. I have been going through and looking at places where I can use freeze in there. Probably the most effective solution is to switch to the 64-bit compiler. Right now, that will get you going. In fact, I think kind of 32 bits is dead, rapidly becoming obsolete anyway. So I don't see real big issues. 64 bits is the future.
A small comment on that. I think the latest version, it has a switch -low-mem that enables the garbage collector for the DMD compiler. So, but don't expect dramatic improvements because the compiler still has to keep all the syntax tree and its analysis in memory. So, but maybe 50% memory can be freed while compiling. So it uses that less memory at the cost of maybe 10–20% loss of performance.
Now the CTFE, compile time function execution, leaks a lot of memory. And when you use a program or compile that needs a lot of CTFE, it does leak a ton of memory. And I've made some changes to the interpreter to eliminate or to recycle the memory used for temporaries, but it's clearly not enough.
So with allocating and then never freeing in the compiler, it does make the compiler very fast, right up until the point where you're paging in order to carry on compiling.
Right. But memory's cheap. Put more memory in your computer. But you're right. Okay, I guess we're out of time. So thank you. Thank you.